All right, for my transient thermal problem, I chose 5.47. The problem states a plastic coating is applied to wood panels by first depositing molten polymer on a panel and then cooling the surface of the polymer by subjecting it to airflow at 25 degrees C. As first approximations, the heat reaction associated with the solidification of the polymer may be neglected, and the polymer-wood interface may be assumed adiabatic. The thickness of the coating is 1 millimeter, and it has an initial temperature of 200 C. How long will it take for the surface to achieve a safe-to-touch temperature of 42 degrees C? If the convection coefficient is 250 watts per meter squared Kelvin, and then what is the corresponding interface temperature? And then the thermal conductivity of the plastic is 0.25 watts per meter Kelvin, and the diffusivity is 1.2 e to the negative 7 meters squared per second. So just running through important aspects of that are the starting temperature, or the ambient temperature, starting temperature, and target temperature. The parameters given of the material itself, and the geometric qualities like length. So for our assumptions, we have the adiabatic interface. We're going to neglect the phase change and any thermal math related to that. No generated heat, 1D conduction, and we're going to do uniform conduction and or convection with just it sketched out again there. So first off, as always, we're going to start out with the Biot number. Just running through the convection coefficient, the length, and the conduction or conductivity. We get equal to around 1, or 1 exactly. So using that 1, we can go ahead and go into the book's tables and look up a lambda and c value for which we get those two values. So then running down here, we're going to go and move on to Fourier's number. To solve for that, we're going to go ahead and start off with the dimensionless thermal equation, or temperature equation, theta naught, which is equal to C1 e exponent to the negative lambda squared of Fourier's number, which is also equal to this equation right here, T minus T ambient all over T initial minus T ambient, which we know all of those, so we're going to go ahead and solve for that number there. Then, because we have that number there, we can go ahead and back solve for Fourier's number using the rest of the numbers we have there, because as we know, lambda, C1, and we just calculated the dimensionless temperature. So just doing that math here, we get a Fourier's number is equal to 3.2975. Using that, we can then plug that back into the original Fourier's equation and solving for time. So if we do that, we get about 27.48 seconds for the entire process to reach 42 degrees C. Then, moving on to the second part, we're going to go ahead and go back to this dimensionless parameter and add a cosine lambda to get to the interface, as that is equal to the temperature of the wood at the interface minus temperature at ambient all over temperature initial minus temperature at ambient. So solving that one through, as we know, all temperature values, and now we know that dimensionless parameter, we'll solve that and we'll get 36.08 degrees C. Thanks.